So this is Chapter 6, Lecture 3. Open up to the page we were on before, where we see the periodic table and the number of valence electrons. We're actually going to skip ahead to the next page and cut right to the chase. This is what you need to know for the first trend in the periodic table. Size. What happens to the size as you go down a group and across a period? So we can see as you go down group 1, the size of the atoms increase. That's the first thing you have to know. The next thing is, as you go across a period, the size of the atoms decrease as you go from left to right. You have to get that into your brain. That is the most important thing. Everything we do depends on that. So if we go back to the notes on periodic trends. Now, in the latest model, an atom has an electron in a region of probability. So it's more like a cloud. But we're going to think of the atom as a shell, as a sphere, for the sake of argument. Our first trend is in atomic size. Atomic size generally increases as you go down a group. This is because electrons are added to successively higher principal energy levels. Which are the shells, or the orbits in the Bohr model. Now, as you go down a group, you're also increasing protons, and protons love to pull electrons closer in, making the atom smaller. But these outer electrons are so far away that the size of the atom keeps increasing. So if we look at lithium with electron configurations, it is 2-1. Sodium is 2-8-1, and potassium is 2-8-8-1. So we see we're just getting larger as we go down the group. As we go across a period, there's also a trend. Atomic size generally decreases. As you move from left to right. Now the principal energy level remains the same for the electrons in the valence shell. But there is an increasing nuclear charge because we're adding protons. The atomic number is increasing. So we're adding a nuclear charge that pulls the electrons closer to the nucleus. So if we were to draw lithium, we have a nucleus, we have 2 electrons in the first shell, and we have an electron in the second shell, or principal energy level. There are 3 protons pulling the electrons closer to the nucleus. Carbon is 2 electrons in the first shell. Be careful how I draw this, how you draw this. We want this to be smaller than lithium. It has 4 electrons in the second shell. But there are 6 protons that are pulling the outer electrons closer to the nucleus. Neon, we have a nucleus, we have the 2 electrons in the first shell, and be careful, we want this to be even smaller than carbon. There are 8 electrons in the second shell. All of these are in the second period, but neon has 10 protons, and those 10 protons pull the electrons of the second shell in closer. We're going to skip ahead and find ionization energy. You have to know the trend of size to understand the trend in ionization energy. When an atom gains or loses electrons, it becomes an ion. Remember, we discussed that. The energy required to remove the first outermost electron is called the first ionization energy, the energy to remove an electron. So a group trend. As you go down a group, the atom gets larger, the outer electrons are farther from the nucleus, so they're easier to remove. So the first ionization energy generally decreases as you go down a group. But within a period, as you go from left to right, the atoms are getting smaller and you're getting more protons that can pull on the outer electrons. So it's harder to remove an outer electron. So you need more energy. First ionization energy generally increases as you go across the period from left to right. So here we see, here is group 1. And as we go down the group, the ionization energy decreases. Here, we're going across period 2. And you should look at a periodic table and make sure that makes sense. Across a period, ionization energy increases. So we have an inverse relationship. As size increases, ionization energy decreases. Another trend, we're going to go to the next page, is electronegativity. Electronegativity is the attraction an atom has for electrons and the electrons of another atom in a bond. So where ionization energy is the energy you need to remove an electron, electronegativity is how the atom itself holds onto electrons. But it's the same relationship. It's the same trend as ionization energy. Electronegativity generally decreases as you go down a group. Your outer electrons are farther from the nucleus. You cannot hold on to them as easily. As you go across a period, electronegativity generally increases. You have more protons and you're holding on to the electrons harder. Because fluorine has a strong tendency to attract electrons, it will attract the electrons in a bond, or it takes them completely. Cesium has very little attraction for electrons. It has a low electronegativity. It will lose electrons to anything near it. Therefore, the lower left corner of the periodic table is the most active metals. These are the atoms where the electrons are lost the easiest. The upper right corner, but not the noble gases, are the most active nonmetals. So fluorine is the most active non-metal. So activity is either judged by gaining electrons easily or losing electrons easily. So fluorine is the most active nonmetal, and francium and cesium are the most active metals. And I believe that is it for today. I'll discuss this more in class because I know it is a hard topic. But other than that, have a great day, and we will see you tomorrow.